Maxima and minima problems, word problems. We had a bit of a look at this idea back in quadratics, you might remember. And what we did, we reduced the word problem down to a quadratic equation. And we said, well, why that is useful is because we could always find the maximum or the minimum by looking at the vertex of the parabola. That's terrific if it's a quadratic. What if it's not a quadratic? This is where we could now use calculus, because we can still reduce the problem down to an equation. And if I'm looking for a maximum or a minimum, now I can use calculus to locate stationary points. And then stationary points, I'll then use the second derivative to work out whether it's a maximum or a minimum to our problem. So they're basically our word problems. So what we're going to try and do with our word problems, we're going to reduce it down to a set of equations. Usually we'll end up with two equations. Sometimes there might be more, sometimes there might be less. But of those two equations, it'll be obvious what we have to find, because somewhere in the question they'll say, find the maximum profit, or find the minimum surface area, or something like that. So I'll be really explicit what the maximum or minimum, whatever it is, we'll try and find. So we need to come up with a formula for that. The other one might not be as immediately obvious, but it might be some other piece of information given to you in the problem. Say it was an area question, they might tell you the perimeter of the shape is something. And so then that could give you some information about the dimensions that you're dealing with. Now once you've got that, we then need to rewrite it as an equation in terms of one variable. And so that's where the extra piece of information sometimes is handy, a bit like the parametrics that we just did. We eliminate some of the variables so we can come up with an equation we can work with. And then we go and use calculus to find maximum, minimum, whatever it is we're trying to do. So, okay, here's a very common problem. I'm sure you've come across this type of problem yourself in day-to-day life. You've got a rope 36 metres in length, and you cut it into two pieces, because that is, of course, what you would do if you had a rope 36 metres in length. Now, the first piece you're going to make a square out of, because it's quite an interesting shape. And then the other, I'm going to make a rectangle. Oh, but not just any rectangle, no. One of the sides of the rectangle will be the same length as the square. As I say, I'm sure it's something you've done yourself many a time. We want to do it in such a way that the length of the square maximises the sum of the areas. So we've got to find what length of the square would maximise the sum of areas. Now what we could do is we could draw up a graph and plot points and go, okay, well, when the square's this length, the area is this, and so on and so on. You'd end up with a curve. But rather than doing that, albeit I know you love drawing your graphs, let's just find the equation. So, okay, there's my square, and my rectangle, which you'll notice has one side the same length as the square. Let's give it some dimensions. Let's be creative here. For square, yes, S. S for square. Now my rectangle, well, one side's going to be S. What shall I make the other? R for rectangle. Okay. Now we want to form two equations. One of those things is what we're trying to maximise. And in this case, it's the sum of the areas. So we'll come up with an equation for that. And the other one is a piece of information given to us. And the only other concrete piece of information I've been given is that the rope is 36 metres long. So somehow I'll tie that in. All right, well, some of the areas, well, S squared plus RS. Okay, brilliant. Problem is I've got two variables there. I want it in terms of one variable. So that's where the other piece of information will come in handy. The perimeter of the whole shape, or the length of the rope, well, my square would be 4S. My rectangle would be 2S plus 2R. So all up I've got 6S, 2R is 36. So the question then becomes, which variable shall we try and get rid of, the R or the S? Want to go for the R? It would seem the logical one. I mean, it looks like the easier of the two. So over in the other one, I'll make R the subject. We get R is 18 minus 3S. Substitute it into my area formula, and we get Tidy it up, there it is. 18s minus 2s squared. It actually did turn out to be a quadratic, this one. That now gives me two choices. I could go and use my theory of quadratics to find the vertex and do all that. But I'm not going to do that because that would make it a silly example for calculus right now. So I'm going to do it the other way. I'm going to use calculus. Okay, there's area. If I'm going to use calculus, I'm going to need my derivatives. So dA ds would be 18 minus 4s. And I'll find my second derivative as well. d2a ds2 is negative 4. Okay. We know stationary points will occur when, not dy dx, this time it's dA ds is equal to 0. See, who says we don't have variety? We can use all sorts of letters. 18 minus 4s equals 0 gives me s is 9 on 2. Okay. Got to confirm that that indeed does give us a maximum area though. So let's have a look at our second derivative. Second derivative, negative 4, concave down. Yep, I'm up the top. So yes, indeed, when the side length is 4.5 meters, the area is a maximum. Notice in the question, it didn't actually ask us to find the area, so I'm not going to waste time working that out. The interesting thing though, when you look at it, if the side length of the square is 4.5 meters, how long does the rectangle turn out to be? Yeah, 4.5 as well. Actually turns out my rectangle is also a square. And you'll find this a lot with these maximisation problems, that well, for want of a better word, the perfect shape will always maximise the areas. Let's make a bucket, because buckets are fun. You've probably heard that term before, buckets of fun. You heard it? An open cylindrical bucket is going to be made. Now, we've got some material which conveniently we've worked out to be exactly 12 pi units squared. How lucky are we? We're going to find the height, the radius, and the volume. And in fact, we're so good at this, there will not be one bit of wastage when we cut our shape out of this material. We'll actually use 100% of the material. Like I say, a real world problem here. Okay, there's our buckets. Radius r, height h. We know the volume of our bucket will be pi r squared h. Pi, of course, is a constant. Again, I've got two variables there. I've got r and h. I want to get rid of one. So there must be more information. And it's our surface area. Surface area of a cylinder or a bucket is, who remembers? So it's just 1 pi r squared plus 2 pi r h. Okay. What would you like to make the subject of this formula to make life easy for ourselves? R or H? H, did I hear someone say? I'm glad you said H, because that's the easy one. R would be very tricky. Oh, look. Oh, told you we were lucky. Notice, pi's in everything, so it'll cancel. Lucky our material is 12 pi units. So let's make H the subject, and we get 12 minus R squared all over 2R. Substituted into the volume. So volume pi r squared times 12 minus r squared. Expand that out. This time we've got a cubic. Okay. So I couldn't use my idea about using the discriminant or finding the axis of symmetry or all those sorts of things. So I've got no choice here. I've got to use my calculus on this one. So 6 pi r minus a half pi r cubed. Let's differentiate it once. And we'll differentiate a second time. That should be all I need to solve this problem. Stationary points occur. In this case, it's dVdr equals 0. Solving that, I get two possibilities. Radius is plus 2, or the radius is minus 2. Because it's a cubic, I guess we've got one of those ones that has a maximum turning point and a minimum turning point. So one's going to be at minus 2, one's going to be plus 2. We've got to find the maximum we wanted, didn't we? Logically, which one shall we check? Yeah, because it would be horrible if the maximum turned out at negative 2. So I challenge you to try and make a bucket with radius negative 2. It would be a little bit difficult. So when we sub in 2 to our second derivative, we end up with minus 6 pi, which is negative Here I am at the top again. Yep. So, right. When R is 2, V is a maximum. But this time, they have asked for more information, not just the radius. So let's find the other dimensions. Subbing into the H1 that we found somewhere, 12 minus 2 squared on 2 times 2. Oh, it also turns out to be 2. And the volume turns out to be 8 pi. So there's our answer. The maximum volume is 8 pi units cubed, and it happens when the radius and the height are both 2 units. It's quite a strange bucket if you think about it. It's going to be twice as wide as it is high. It's a rather odd bucket. Okay, 10 evens, but don't do 30. That would be slack setting all of the evens. So we won't do 30. And then 10i would do the evens as well. See, how nice am I to you? I'm not making you do 30.